Hello, my name is Sara Vasquez. Today I'm presenting to you the project for Big Data Analytics, Case Study in Web Analytics, Machine Learning applied to Application Performance Monitoring for Anomaly Detection. Application Performance Monitoring is widely used in the industry to measure end-user experience for web applications. With the highly spread out web applications offering as a software as a service in the cloud, the volume of data generated is enormous and growing every day. The multiple options offered by Saas providers to millions of users increase the complexity of performance analysis and performance problem detection. The use of common statistical methods to identify performance problems in the web application is becoming obsolete, demanding to have a solution that allows to identify performance anomalies in near real time. Application Performance Monitoring, a quick overview. Application Performance Monitoring, also known as Application Performance Management, consists in tools that help to manage availability, performance, and user experience of an application. The main goal of an APM application is to diagnose and detect complex application availability and performance problems. Beyond the use to identify and troubleshoot performance problems, an APM application can also be used to determine application usage patterns and volumes. At the end, an application performance monitoring should provide metrics like amount of transaction processed, usage patterns, response time to process transactions, with detailing response times across different components, and component monitoring. Gartner has defined 5 dimensions for managing application performance. Analytics and reporting is the ability to collect raw data from other toolsets that allows to answer a variety of performance questions, usually using standard statistical methods. Component monitoring is the capacity to monitor different components used by the application. By example, a database, databases, application layers, integration layers, usually tailored to help on root cause analysis. Business transaction is the ability to map the technical aspects of an application, by example, a web page, to the business context, usually with the goal to define SLAs. Runtime application architecture. It maps the user transaction to different components in the application, but in this case, is tailored to infrastructure components like networks, servers, cloud components, etc. Finally, the end user experience, which provides most of the value for an APM solution. It gives details about what is the experience of the user using the application, using agents, and information from the other dimensions. Our project is based on information generated in this dimension. Summarizing the problem and what is proposed. Problem statement. Due to the high number of combinations of factors that can affect the performance of a SaaS application and the high volume of data generated every minute, the use of traditional statistical approach is less than ideal for near to real-time identification of performance problems or anomalies based on user experience. Proposed approach. To use machine learning techniques on big data that can help us to identify anomalies in user experience and provide detail which offers potential reasons of what is causing the performance problems. Problem statement. APM data is the perfect source of information to determine the end user experience while using a web application. Now, in the context of a SaaS offering, there are multiple implications and combinations which will affect the end user experience. By example, multi-tenancy. The same software is used but customized in endless number of ways and from different customers, causing different performance behaviors. Multi-client support. A cloud solution is expected to be used by different type of clients. By example, desktop applications, different UI versions, browsers, operating system, native and hybrid mobile applications. Network. A cloud solution is accessible over the internet. It is expected to be used from multiple locations around the globe under different network conditions. Application complexity. Large number of screens and actions to be executed within those screens cause a very high number of combinations and actions available within a SaaS application. APM data used in this project. APM data is a big data. By example, every record in this dataset has an average size of 3 kilobytes. Data coming from over almost 5,000 different tenants across 6 different data centers. This generates an average volume of 210 million user interaction records per month, with a peak of up to 1 million user interactions per hour. The raw data generated represents around 600 gigabytes per month, and with an average increase of 10% every month, This is real big data. Here is an example of a typical record containing APM information for a single user interaction. Information like tenant, location, browser type, OS type, and different response times and client types is presented in this type of records. In this case, we are focusing the analysis of end-user experience data, which contains metrics for multiple components like client time, network time, server time. It does include KPIs like end-to-end response time, time to interact, but it also includes characteristics like browser type, client and device type, number of round trips, OS use, network type, and tenant. Raw data. One month of data was loaded from the APM Data repository into Elasticsearch for the purpose of this project, loading about 22 million records for 1 month of data from 7 different cloud tenants using Python, the Elasticsearch API for Python, Pandas, and the Request API to extract the data from the APM repository. Response variables. Let me give you a small demo using Kibana on how those response variables look. This is a Kibana dashboard. The first chart shows the average values for different metrics over a period of time in 1 week. By example, the average server response time, the network response time, or the average client response time. Similarly, on this other chart, we can see the average values for KPIs like end-to-end response time or time to interact. But also we can observe some other statistical measurements like 90 percentile or 95 percentile for time to interact. At the same time, we can observe the number of interactions per hour. By example, in this case where in October 1st, we have a peak of almost 1.5 million user interactions on that 1 hour. Finally, we can see the details for each user interaction, either from the number of times that it was executed to the average time to interact and the other KPIs and metrics observed in this dashboard. Let me talk about the response variables. TTI, or time to interact. It represents the time that it takes for the application to be ready to interact with the user after a previous interaction. E2E time, or end-to-end time, represents the time that it takes for the user interaction to fully render the results in the screen. Client time is the time spent on the client, by example the browser, the mobile application, or any other UI. Network time is the time spent in the network to send the request from the client to the server and receive the response from the server to the client. And finally, server time is the time spent in the backend executing required logic to the server request. In this case, it could include application logic, database access, or any other component like asynchronous web service calls. Features variables in a Kibana dashboard. We have defined 7 different features to be used for prediction, where 6 of them are categorical values and 1 is numerical value. This Kibana dashboard shows the 6 different categorical features. Here, to start, we have the device types. We have 5 different device types that goes from default, which represent a regular PC, to a Windows Touch, iPad, Android, or an iPhone. As it was mentioned before, we extract data from 7 different tenants from the entire APM database. We also have over 4,000 different combinations of screens and actions executing within that screen. The next one is the network type. As it was mentioned, this is another common aspect of a Saas solution, where a Saas solution is accessed from different network locations with different network types. Then we also capture the OS type, by example Windows, iOS, Android, Mac, etc. Finally, as a categorical feature, we also have the UI type and browser, which is basically the combination of the different UI types and the corresponding browser if this is a browser access application. Finally, we also have one numerical feature, which is the number of round trips. This represents the number of HTTP requests required to execute the user interaction. Initial exploratory data analysis using Kibana. In this dashboard, we can see simple statistics for the different response time variables, or what we will call labels in Spark. By example, time to interact. As you can see, the mean and the max and even the percentiles are showing a very big spread. Not just time to interact, with other variables like the network or the server time, and showing weird numbers, even negative numbers. Now, let's look this over time. This dashboard shows similar data in a time series fashion. As you can see, the 95 percentile is also showing big variation. By example, on October 17, we are seeing a very high 95 percentile of time to interact. But maybe this is what we want to catch and have some insights on what is happening as part of this exercise. Definitely we're going to need to do some cleaning of outliers to have stable models. Detailed explanatory data analysis and cleaning using Python, Pandas, NumPy, and Matplotlib. The whole data set considered is about 22 million records. In preparation for modeling, the following was done. For further data exploration and to work with Python, we created a subset of data from October 1st to October 5th. As a web application, the performance of the application heavily relies on proper caching mechanism in the client and the server. The APM application captures called client and server scenarios. In the entire month of October, they represent about 8% of the user interactions. Due to that, we are removing those cases from the dataset. As we have over 4,400 different user interactions, we are restricting the analysis for the top 10 user interactions. We are using Python Elasticsearch Client to extract the data from ALK into Python, and we are using Pandas as a main API to handle the data within Python, including the API to convert from JSON to Pandas data frame. With the data subsetting mentioned in the previous slide, now we have over 750,000 records. While looking into the scripted statistics using Panda, we can still see high variation for those different response variables. Now, let's look into moving average. Using Matplotlib, we can chart those moving average, including an area chart with one standard deviation, which still shows high variation. Using an histogram, we can see the long right tail which the TTI response time distribution has. Let's do not forget something. This information is an aggregation across 10 different user interactions which represent different screens and different actions within those screens. Trying to alleviate that problem, let's use a violin chart for time to interact for each of the top 10 user interactions, still showing a high spread. Further data cleaning of data by removing outliers using IQR. Using IQR and the interquartile range rule to detect outliers, we can define that anything above or below 1.5 times the interquartile range is an outlier. And this rule was used to remove outliers based on a TTI, which represent about 5% of the total data. With this, we have a more suitable distribution that is showing these violin charts. Now let's talk about how we load the data from Elasticsearch into Spark. Load data from ALK into Spark. To load data from ALK into Spark, the standard ALK connector for Apache Hadoop 6.5 was used. More information about this connector can be found in the link. The library is used as any other connector library, but it has some challenges as the documentation was not clear on how to use it on a Spark data frame. Let me give you a demo on how you use PySpark to load data from ALK. First, we need to start PySpark with the corresponding libraries and configuration. Then, we need to load some libraries. The next step is to prepare some variables that will be used during the construction of the query. Now, here we have the construction of the query. The query is similar as the query used in ALK, which is in JSON format. Now, we can execute the query and load the data into a data frame. And finally, like any query in Spark, the query doesn't materialize until you actually try to retrieve data and show it in the screen or to process it.